in between, I'm thinking about things like, there was this old book by Marty Hersford, full-part relationship, where she looked for certain lexical patterns. X is A, X, Y, and other Z's. So you could maybe come up with things like that for verbs, where particular function words or particular known pronouns or whatever, fill certain slots. And is there any word like that?
We didn't have time to really experiment with that whole space, so yeah, we did go with extremes because we kind of wanted to, map it out a bit. One particular one that I wanted to work with that I never got a chance to was unsupervised part-of-speech tags, for example. But the answer is no, we didn't get a chance to experiment with a lot of, the point was to leave it as open as possible so that people could plug in kind of whatever is available to you for the particular domain you're looking at, because there's a wide variety of resources available depending on where you're looking. If you're looking just at biochemistry, there are tons of annotated resources out there that you could use to get a really good parser for. But if you're looking at hematology or something like that, there might be nothing. You might not be able to get good parsers. So we just wanted to leave that as open as possible.
So another question. So you said you're doing almost class parsing, which I assumed you were talking about the constituency parsing. But here it looks like you're using dependency trees.
Yeah, that's a good question. We tried a few different parsers. So we tried, I'm not sure, I'm not positive which one we actually ended up using, but they all showed the same performance approximately. So we used the Stanford parser, the unlexicalized model of the Stanford parser. Okay. The CNC parser, which is the CCG formalism, and we used the RASP parser. So I think so RASP is a dependency parser, that's what I'm showing here, I think. Okay. Yeah, so that's okay, so like I said, we add some probabilistic structure to explain how these variables relate to one another. Verb over frame and frame over observation are sets of categorical distributions. So the story that this is telling is that when I see a particular verb instance, I choose its syntactic frame from a verb-specific distribution over syntactic frames. So basically you can think of the verb node as indexing into that verb over frame node. And then I choose each syntactic observation that I've seen from a frame-specific distribution over observations. Now this is very, very similar to latent Dirichlet analysis or allocation. Basically, if you think of the syntactic frame as being the concept and the syntactic observation as being like words, you get something very similar. And then, of course, it needs to have priors on these distributions so that we can do Gibbs sampling for inference, and then we just count up and normalize the verb by frame counts to get our distributions over frames for each verb. And so you might end up with something like this. This is something that I think kind of corresponds to a transitive frame that comes out of the system. This shows the probability mass placed on different syntactic observations. This particular frame often occurs with verbs like stimulate, conserve, and eradicate, and it's high probability on subjects and direct objects. One problem you might notice with this setup is that the categorical distributions are actually incapable of perfectly capturing the notion of the transitive frame, because you would want to be able to specify that there has to be a subject and there has to be a direct object. But it's incapable of doing that because it's taking its mass from the same pool of probability and it has to normalize to 1. So all it can really do is place as much mass as it can on both direct object and subject. So that's a shortcoming. We experimented with some other variations of this model that used beta and Bernoulli distributions to determine the presence or absence of syntactic observations, and there was a slight improvement in performance. Yep.
So just to make sure I'm understanding correctly, so this is a distribution over just a single particular argument that are generated.
No, this is actually this is one of the shortcomings of this simplification is that syntactic frame only has one distribution, and it applies that same distribution for all the arguments it chooses. So it doesn't have a separate, it doesn't have a way of saying I want 100% have a subject and 100% have a direct object. It basically just give a distribution that allocates as much weight as possible to both of them.
Yeah, so it's a distribution over the set of potential arguments that any verb could take.
Right.
So but another thing you could have done is done distributions over tuples, right, where the tuple represents an instantiated frame, right? So like one of the objects in your domain then would be like generate a subject and an object and an indirect object.
Right, right. So that would be have a much larger set of things. Right. Yeah, that's definitely a possibility.
I mean, it's kind of more like what I think about when I think about a frame. I think about it as like a tuple of arguments that are all associated with a verb.
That's a good point, and I think that what I mentioned with the just kind of having binary values for whether it occurs or not, which is basically the second iteration of this model that we tried, accomplishes something similar. So it's kind of learning the tuples and at the same time, right? So you basically get something that says assigns 100% probability to having a subject and 100% probability to having a direct object. So it's similar. So to evaluate this, we need to find a task-based evaluation because this unsupervised output is hard to line up with the existing methods where they have predefined frame inventories. So fortunately, we have verbs clustered according to alternation patterns, which is a syntactic phenomenon syntactic semantic phenomenon that's known to correlate strongly with syntactic frames and has been used for over a decade for evaluating these things. So there was a well-established evaluation method for this. And the basic idea is that we'll cluster our verbs using their distribution over syntactic frames as the features. And so we don't have to worry about what our actual inventory is. So we can cluster an unsupervised method just as readily as we can a supervised method. And then we can, so we did this with using k-means and the gas statistic for choosing the value of k. And then we can just compare these clusterings to the gold standard using any cluster evaluation metrics that we have. So that's what we did. And the first thing that we compared was we looked at how our system, which we're calling GraphMod, compared to Perform versus Valex on general language, which is where we expected Valex to be strongest. We used features, so this is using the parsing features method for finding syntactic observations, but it uses less information than the Valex rules, the handmade rules. And we consistently outperform Valex. This is just a few different clustering metrics because they can be a little quirky. So adjusted rand index, purity, and normalized information similarity. And so we outperformed across the board, and I think most crucially is it took an order of magnitude less effort than Valex would have required for writing all of these handmade rules out for extraction. We then looked at how we performed on biomedical data. We compared to BiLexicon, because if you remember, that was by far the top performer compared to Valex. And we looked at a few aggregated subdomains. And again, we got best performance across the board. So those were good results. We also tried towards the end of the study, an augmented model where we tried to bring in semantics. So in this model, you can see that not only do we model syntactic frames and producing syntactic observations, we also model a semantic frame that combines with the syntactic observation to produce a semantic class and semantic observation, which is essentially a little bit of distributional semantics that we put in, kind of coming off of syntactic observation so that we can learn argument and verb specific semantics. And we weren't able to run that on the very large data sets that we did with the simpler models, just performance issues at the time. But running it on the Wall Street Journal data, I just wanted to show kind of qualitatively, these are some of the semantic classes that we got out of it, which make a lot of sense in the context of the Wall Street Journal. So we have classes that correspond to financial units, to corporate leadership, verbs of modality and prediction, and adjectives and adverbs that are related to market direction. So that was kind of cool. And there was a bunch of other work that I had to gloss over, didn't really cover in depth. So there's a broad study of linguistic variation in biomedicine that I mentioned, where we looked at 11 different feature sets and 38 different subdomains. We produced the first annotated gold standards for syntactic verb frames in biomedicine. We did the performance studies of the existing state-of-the-art. And at the end of the study, we released comprehensive syntactic lexicons built using our system for both general language and a number of biomedical subdomains. And this produced 3 articles in bioinformatics journals and a co-link in an ACL paper. Okay, so that was my dissertation work. Now I'm going to talk a bit about my current work on morphology of low-resource languages. This is part of the Babel project, which I think you're largely familiar with. The motivation behind this study is speech recognition for low-resource languages, speech recognition and keyword search. The motivation here is that many of the kind of less studied languages are becoming more and more important to various people. This graph shows projected growth of various areas of the world in terms of their share of mobile data, and of course, Africa, the Middle East, and Asia are growing very rapidly. This program was designed because government analysts need to be able to search audio for important terms. Even if we don't have linguistic resources for these languages, supervised data for training models or native speakers. And in the extreme case, the setup of this study is that we're given 3 hours of transcribed audio, and we're asked to train an ASR and keyword search system in a matter of days. And then we're evaluated with a set of search terms with this term weighted value metric. And so I'm looking at a particular issue that arises when we have such limited training data, which is that we have very poor vocabulary coverage. So this shows the out-of-vocabulary rates for the 6 languages we're looking at this period. So in types, tokens, and in the search terms and keywords. And of course, there are a lot of things that this affects about the pipeline, but in particular, so the language model, if it doesn't know a word, is going to have to back off to some sort of estimate, back-off estimate. And the other issue is that if we have an OOB keyword, that's never going to match in the word lattices, so we're going to have to back off to something like a phonetic search, or like a confusion, phone confusion matrix or something. So how can morphology help with this poor vocabulary coverage? Well, like I said, we're usually looking, ideally we're looking for a search term that we know, that is in the, that could potentially be in the word lattice that we're getting out of the ASR system. So if we're looking for, so we'll have several paths that we can take that correspond to different transcriptions of the audio data. And if we're looking for walking, we can just see if it's in that lattice, and then there'll be scores associated with it, and we can just kind of decide if does this meet the threshold, and if so, we'll return that as a match. But if a word is OV, it's never going to show up in the word lattice. Maybe something else will show up that sounds kind of similar, and then we might be able to match that if we have, say, a confusion matrix of how similar different phones are. I believe that's how the Attila system is backing off in the vanilla case that we were given. So our idea is that instead of a word lattice, we could build a morph lattice if we have a segmentation of all the words. So in this case, we wouldn't have to have seen the word walking. We would just have to know that, we would have to just know that there's a morph walk and a morph in. It's something about the probability of the sequencing. And we could construct a lattice like this. And then we can just look for the segmented search term rather than the search term itself. And so we use this as a sort of back-off, similar to, so I mentioned that in the vanilla system we're going from a word lattice and just doing something phonetic. This is kind of an intermediary back-off step. And the evaluation metric, that term weighted value, encourages this because it heavily penalizes completely missing a low-frequency term. So if you don't find it in the word lattice, you're strongly encouraged to look as hard as you can to try to find at least something to return. And so we did some initial experiments, and we found that we got a nice improvement. So the The base column is just using the phonetic backoff, and then the morph column is using that morph backoff. You can see that we get a boost. So the question now is, how do we learn these segmentations? Well, when you look at how, if you look at a textbook and look at how they represent word segmentation, it seems like it's sort of tree-like structure. So, of course, the first thing you reach for is a PCFG, the first thing that comes to mind. You might write a grammar like this, and you hope to get something like this kind of structure out of it if you train it right. But unfortunately, this isn't the case. There are a lot of things wrong with this. So the first thing is that this should really be prefix cares, stem cares, and suffix cares, because this isn't even assigning different probabilities to some characters. This isn't even distinguishing between prefix, stem, and suffix in terms of probabilities. But even more importantly, there's no way to assign different probabilities to this particular decomposition and this one, just because of the independence assumptions for PCFG. So the way that we get around this is with something called adapter grammars. And what an adapter grammar does is it takes the PCFG formalism and it says, okay, some of these non-terminals are going to be what we call adapted. And these are the underlined ones. And what that means is that an adapted non-terminal has two possible ways of expanding. It can either proceed like a normal PCFG with some probability, and then its ultimate probability will just be include the product of its children. Or it has the option of immediately choosing a complete sequence of terminals that it has seen in the past. So we maintain a cache of what this particular non-terminal has expanded to ultimately in past applications, and with some the hyperparameters determine how likely it is to just jump to one of those. And when it decides to jump to one of those, it then picks it with proportionally to the number of times that particular expansion has occurred. So this means that it can remember and prefer common sequences that it's seen in the past without having to also upweight all of the permutations of it. So it can remember ing is a good expansion of a suffix without having to also boost NGI and all the other permutations of the characters. So this lets us keep the intuitive formalism of PCFGs, but also get around this problem. And this is important keeping this intuition is important because in this study we're allowed to use some scholar-seeded knowledge, and by that I mean one of the evaluation tracks involves knowing some kind of coarse properties of the languages in question. So we might know that a language is Semitic, or that a language is analytic, or that it, various things, that it has vowel harmony, so things that you would get if you kind of picked up a textbook, a linguistics textbook on the languages. And we wanted to be able to experiment with writing different grammars that exploit these kind of little specific typological tidbits that we might have for the languages. So now I'm just going to go into a few ways that we're working on doing this. These are all various stages of completion. Some don't even have numbers associated with them. But it's just to give you an idea of the sort of things we're interested in doing. And I should also mention that I think that a lot of these coarse properties can be discovered with simple statistical tests. So I'm not even sure it's that important that I think that for something like determining whether a language is agglutinative, for example, I think that you could probably write a fairly robust statistical test that just can tell that by looking at a bunch of data without actually having to look it up in a textbook. So it could be useful in that way as well. So how do we use the linguistic knowledge in these adapter grammars? Well, if we know the language is agglutinative, that means that the prefix and suffix aren't just single morphs, which is a good assumption for a language like English, but rather a potentially very long sequence of independent morphs. So we might want to add that layer of indirection here. If we know that a language has vowel harmony, we might want to, we might have a chart like this from a textbook. It tells us something about the properties of the characters, and we might be able to do something to encourage sequences of morphs to share the same properties of those characters at the vowel level. One thing that I'm particularly interested in is joint inference of morphology in word classes, part of speech tags, and this can be also coded up in PCFG-like formalism using kind of dummy non-terminals that kind of pop off part of speech tags as they go along, and then you have the emission probabilities are basically separate morphological models for each particle.